their existing designs are able to satisfy all of these constraints.
We have to design and construct a balsa wood prototype for a truss bridge with the maximum load supported to a bridge weight ratio. So we're going to weigh our final bridge, and then the weight that we hold has to be 500 times the weight of our bridge.
1/16 inch balsa wood. The bridge must cross a span of 45 centimeters. The bridge must be bottom loaded. No portion of the bridge may extend below the testing surface. The bridge must be able to accommodate a 5 centimeter by 5 centimeter loading block assembly. Glue is the only permissible adhesive.
We about to build a bridge. So we started out using Bridge Designer, but that wasn't practical because we needed the tension and compression forces that were acting on each member. So we started using MD Solids 4.0, and first of all, it was really hard to use, and we didn't know how to get it how to make it stable. So we looked online at some basic pictures, and Vonta ended up innovating this design we found, and it was really cool and it was really tall. But the MD Solids has little rectangles, and we're working in centimeters, not inches. So Vonta built the bridge, and it worked, and we tested it on the computer, and it worked really well. But he built it on a 24 centimeter scale, and we needed it on a 48 centimeter scale. So I rebuilt it with Vonta's help, and what we had to do was multiply each member by 2 to get it to the scale that we needed it. And when we tested it virtually, it worked out. So we're about to build it and see what happens. Testing our first bridge, we found out that we didn't have enough members on the bottom to really support the load, and another big problem was we ended up using 1/16 inch balsa wood, so it was really skinny, and it was super hard to cut angles. So what we did was just cut single angles on each piece and then fit them together at the tip, and that helped us out a lot because that way we weren't trying to glue too many things that was unnecessary. So our gluing will be better on this next bridge, and it'll be tested tomorrow morning, so hopefully it works. But yeah, that gluing was our main thing, cutting, and the height was another big thing because our bridge was falling over almost, and it was swaying a lot because it was 28 centimeters tall, and our new bridge is only 13 centimeters tall. This was Thomas's design. Thomas and I built it this afternoon, we actually put 2 supports on the bottom that were 4 centimeters apart from each other to hold the loading block. So we're going to test this prototype tomorrow with the weight coming down the bottom. So when we tested our prototype, it was really crazy because we actually glued one side of our bridge to the styrofoam sheet that we let it dry on. So one half of our entire bridge was not there. It was like testing half of a bridge. So when we put the weight on, the side that was completely there stayed strong. So that was awesome because we built it well, but the other side did not. And there was a lot of bowing going on between the 2 sides. So we decided to add more members, like connecting the 2 main trusses so that it wouldn't bow. We double based the bottom and top, and we glued it on wax paper so that we won't lose half of our bridge this time when we test it. Assuming that we have a top load of 500 grams coming down from the middle member, the sum of our moments was 250 grams on each side. So that's a pin down side and a rolling side. And then because our bridge is made up of a bunch of isosceles triangles, all the angles are the same. So all these angles, like where I drew here, all the circled angles are the same. So this means that because the angles are the same, the forces have to be the same. Because if the forces weren't the same, one angle would be smaller than the other, and so on and so forth. So all of the middle members' forces were 279.02 grams. And most of them were compression, but the other ones were tension, just depending on whether or not it was going up or down. And then once I figured out that, I plugged in the sum of. In order to find members like BD and CE, all you had to do was plug in the points around it that you knew and then find the sum of the forces on the X. So you would multiply all the forces and then use cosine for X and multiply that by the angle. And that is how I found out all the forces that were acting on each member. The main calculation issue that we had with our bridge was that member EG is expected to hold 619 grams of this weight, which is terrible because this means that this member will break first. No single member is supposed to be holding as much as the entire load. So this is why we decided to double up our base. So we have our single base and then a completely extra base to go underneath it to try and help with some of this. As a group, I feel like this was a really awesome project because all three of us went into this not really knowing anything about how to build a bridge, having experience with the wood, the MD solids. None of us were super strong with the calculations, but we all pulled together and we did it, and we put so much work in and time and effort, and we learned from our mistakes for sure. And we all feel so accomplished that no matter what happens with our bridge today, we know that we tried our very best and we're satisfied with that. So we shall see.